month or so ago and explained to them what was going on. So I put it on a test. Because when you get, like, we're getting accredited next year. We're supposed to be this year, but they pushed it back to next year. And they will literally pull kids out of the hall and ask them if they know our mission statement. So on my math test, I put it on there as a bonus question. I said, hey, what's the Fremont High School mission statement? And I'll bet you 90% of my students put stronger together. And so I went down, I said, hey, we got a real problem.
Yeah, where does that mean to be accredited? Like for the high school?
So they literally come in and they grade us.
Oh. Okay.
And if you do not pass accreditation, your diploma means nothing. So, yeah. Yeah, it's kind of crazy. But we've usually done pretty well. So I'm not overly concerned. But, there are schools that don't meet accreditation. So
what is our mission statement then?
Right there. It's been there for 3 months probably. Yeah, you probably ought to learn it. Okay? You guys gonna shut your Chromebook so I can get going or what? You wondered why I was making eye contact with you? I literally just said that, but you were obviously still talking. Okay. Alrighty, so we are going to wrap up chapter 3 today. Lab 10 on Friday. Make sure you do the right pre-lab. I heard somebody talked about doing the wrong pre-lab. Was that you? Somebody was talking about it earlier. Make sure you do Lab 10's pre-lab. This is one of my favorite labs, so hopefully it works out well. Alrighty, so it is 1:27 today. This is 6th period, and this is Chem 1110, Chapter 8, Day 3, and our objective is going to be able to properly calculate dilutions. Is our main goal. We're going to do some other things, but that's our main objective. Now, what does it mean to dilute something, typically? What?
Thinking about like when you dilate your eyes.
Okay, dilate, similar. What does it mean to dilute something? Yeah.
Decrease the concentration.
Yeah, to make it less concentrated, right? Now, the standard dilution equation is this. M1V1 equals M2V2. Now, on its face, this is really simple. They're going to give you what?
3.
They're going to give you 3 of those and expect you to find the 4th, okay? Now, there is one kind of question that they do ask that is a little bit more difficult than this, okay? And I'm going to cover one similar to that and kind of see if we understand it. So usually what they'll do is these are my initials. These are my initials, volume and molarity. These are my finals, okay? They typically give you some initials, give you one of the finals, and ask you to find the 4th thing, right? Sometimes, though, they word a question like this, and it makes it a little tiny bit different. And it says, what is the concentration of adding 82.5 milliliters of H2O to 125 milliliters of 4.2 molar solution? Okay? Now, that'd be a question mark. What you've got to do is you got to go through and figure out which one of these is M1V1, which one is M2V2, and kind of go from there, right? Now, as I look at this, I'm going to add 82.5 milliliters of water. Okay? That's how much water I am adding. Is that either my initial volume or my final volume? It's not. And that's what makes this problem a little bit different. Okay, I'm adding it to this. So this is my what? The 125 milliliters is my what? It's my V1. The 4.2 molar is my M1. Okay, then I need either an M2 or a V2, right? Now, it says what is the concentration. Concentration is molarity, so that's what I'm looking for. So I'm looking for M2. I don't know it. What is my V2, though? How do I find my final volume? Yeah, I'm going to add that to that, right? So it's going to be my initial volume plus whatever I added to it, right? So I add them together and I get what? .207.5 milliliters, right? Now, when I go to my equation, I'm going to say 4.2 molar, right, times 125 milliliters is equal to M2, which is what I don't know, times 207.5 milliliters. Now, typically when we do molarity, what's my volume? We talked about it the other day. Molarity is what over what? Moles over liters, right? So my question is, Richard, am I okay to leave this in milliliters?
As long as you are, as long as they're both in.
As long as they're both the same. Because what's ultimately going to happen here?
You're doing the same thing on both sides.
Yeah, and my milliliters are going to reduce out anyway, aren't they? I do the math, and what do I get my M2 as? So 2.53? 2.5 molar. Why? Yeah, 4.2 molar only has 2 sig figs in it, right? Now, this is where I really try to get, and I'm going to be honest, I try this with my math students, but they do not understand this. Okay, whenever I get an answer, what should you do? Besides circle it. What? I got a unit. It's got a big M on it. I would say at least look at it and say to yourself, self, is there any way that could be right? Anybody got that answer? Why?
Because it would be less than you're adding.
Exactly. My molarity had to go where? Down. Now, it doesn't guarantee me that I'm right, but it does give me an indicator that I could be right. If that was 7, I better be saying to myself, self, I done screwed up. I mean, right? So, yeah, it's just kind of something you need to look at and say, can I or can I not be right? Good indicator there. Good job, Bingham.
So it had to be smaller than 4.2.
Exactly, because I'm doing what? I'm diluting it. My concentration must go down.
It's an inverse relation.
It's exactly what it is. My volume goes up, my molarity must go down. Great point. Okay? Now, from there, we're going to work, especially in the lab. Now, you're going to do a lot of this in the lab, and I'm going to be honest, this is one of my favorite labs simply because, I don't know, I think this stuff kind of fascinates me, and it applies a lot. But colligative properties. Colligative properties. Now, colligative properties are like freezing point depression, boiling point elevation, things like that, right? And the definition of colligative properties is, let's see, properties of a solution that only depend on the concentration of the solute, not the identity. So it really doesn't matter what's in there. All that matters is what? How much is in there. But how much is relative, and I'll explain what that means. So let me show you something, okay? The biggest thing you want to look at is you want to look at the number of ions. Now, when I say that, you can look at ions, you can call them particles, you can call them whatever you want. But let me explain. Let's say I had a 1 molar solution of NaCl and I had a 1 molar solution of CaCl2. These are my two solutions, right? Now, when these two things dissolve in water, okay? Well, when I put these two things in water, the first thing they're going to do is they're going to dissolve, right? As they dissolve, though, who can tell me what else they're going to do? It's another D word.
Associate.
They're going to
Associate.
dissociate. Now, when they dissociate, what will NaCl give me? Anybody know? Nobody? Well, what kind of compound is this? Why is it an ionic compound? Metal to a non-metal, right? Get it? So what happens when they dissociate? It's going to split up into two ions, right? And I'm going to get Na positive plus Cl negative, right? So even though I've got a 1 molar solution, that 1 molar solution is actually going to give me 2 ions each, right? And what about this one? What's it going to give me? Nobody? It's going to give me 1 Ca2 positive and what? 2 Cl negatives, right? So how many ions does this one give me? Nobody? Last time I checked, 2 plus 1 is 3 ions. Which one would be better to put on my sidewalk? Anybody know? Not a soul? Well, look. If this one gives me 2 ions and that one gives me 3 ions, I would always take the one that gave me more ions. Let me explain why. There's this thing called freezing point depression. Okay, freezing point depression. And freezing point depression, and I wasn't even going to discuss this, but you guys are all looking at me with a blank stare, okay, is a situation where it is moles per kilogram. So in this situation, you would have, like, let's assume we had 1 mole. So I got 1 mole of NaCl per kilogram of H2O. Okay? Now when it does that, I'm going to change the freezing point by 1.86 degrees Celsius per, I don't know, let's say per mole of particles. Okay? Now, so if I put NaCl on my sidewalk, how much is it going to change the freezing point of that ice? How did you do that?
Because it's 2 ions.
Yeah, I get 2 particles out, right? So I'm simply going to take 2 and I'm going to times that by 1.86, right? So it's going to change it by 3.72 degrees Celsius. So now my water on my sidewalk, instead of freezing at 0, is going to freeze at negative 3.72 degrees, right? But what's it going to freeze at if I use the calcium chloride? Well, if I've got the same thing, 1 mole of CaCO2, right, per kilogram of H2O is gonna now be 3 times 1.86, which is gonna give me 5.58 degrees Celsius. So which one's better? Yeah, the one that gives you the greater number of ions. Now look at the same thing for sugar. Okay, do the same thing for sugar. Okay, who remembers what sugar is? C6H12O6, right? Now, what kind of molecule is sugar? Anybody remember? Molecule, compound, whatever you want to call it. Richards. Wasn't Richards. Maybe it was Richards. Get us. It was you. What did you say this was? An ionic, because it's a metal to a non-metal. Anybody remember what these were called? It's not ionic. I heard it. Who said that? Fisher. It's covalent. Why is it covalent? Two or more non-metals, right? So it's covalent. Now, here's my question. When I put sugar in water, what does it do? It dissolves, but does it dissociate? It doesn't. So if I put 1 mole of sugar in water, how many particles am I going to get out? Just the one. So how much would sugar change my freezing point? Yeah, just 1.86. Could I use sugar to clear my sidewalk? I could. Would it be as good as salt? No. Would it be as good as calcium chloride? No. Okay, now here's the question. Do you guys realize that you don't really use salt on your sidewalk? What do you use, Kyle? We sold pallets of it, man. What's it called now? Nobody? I'll bet you all have a bag at home, and it ain't salt. Say it louder. It's called ice melt. Why? Why is it called ice melt and not salt? Because it's not NaCl. It's not. Because if I can find something that gives me more ions, I'm going to be able to use what? Less of it to get the same result. I use less of it, I'm going to save money. Ice melt is not salt. Period. Does anybody know why we don't use salt anymore? And it's not that we're running out of it. We got all kinds out there. Anybody? Salt is terrible for concrete. Yeah, it ruins your concrete driveway and your concrete patio and your concrete sidewalk. Okay, well, why do they still use it on the freeway? Because they do. Because most freeways are asphalt. Now, the ironic thing is the new freeway they're building out here, it's concrete. What are they going to have to do? They're going to have to, I'll bet you money, they actually use something else. They're going to go away from using just plain salt. Plus, these other things do a better job. So, kind of interesting. Okay?
Question.
Yeah.
What's the difference between dissolving and dissociating?
Okay, to dissolve simply means to mix in with the liquid, right? To dissociate means they actually do what? Split apart. Okay? Let's talk about that. Okay? Does anybody know what the word for that is? Nobody? It's called solvation. With an O, not an A. You get the joke? You get the joke? Yeah, okay. Solvation. Now, anybody know how to... Why are you furrowing your eyebrows at me?
I don't know. I was looking at
Oh, okay. You had a furrowed brow look like you were confused about something. Okay. So, anybody know how solvation works? Okay, so I got a beaker, right? Beaker of water here. And I put some NaCl in there. NaCl. As soon as it hits that water, the water starts to basically, for lack of a better word, attack it, right? And as it attacks it, it starts to form bonds to it. And it literally tries to do what? It wants to pull it apart. As it does that, there's other water molecules kind of getting down in the nooks and crannies and trying to push it apart. And what ends up happening is that you create what is known as an ion dipole attraction. Okay? So if you remember, water looks something like that, right? Correct? Well, that makes this end of my water molecule quite what? Quite negative. Makes this end naturally then quite positive, right? Well, this water molecule is going to get, and it's going to start to pull the chloride and the sodium apart from each other, right? And then it's going to get in between it. What's going to be over here? That's where the chloride end's going to go. And then the sodium end's going to be over here, right? And that water molecule gets in between them. And because that ion dipole attraction is literally like a truck, and it pulls it away. And that's what splits them up. That's also the reason why the water doesn't freeze again, is because these ions are in the what? But they're in the way of the water molecules getting back together and forming that solid, which is why it has to be colder now. Get the water molecules moving slow enough that it can push them out of the way and create that solid. Okay? And that works with anything, but the more I put in there, now the more I've got in the way, the more energy I can take out, the lower the freezing point. Okay, it works the same way with boiling point. Okay? If I was going to boil some water here, okay, I'm going to heat this sucker up, right? I got a gas bubble starting to form on the bottom of my pan, right? In order for that to boil, that gas bubble's got to get from the bottom of the pan to the what? The top of the pan, right? Well, if I've got a whole bunch of sodium and chloride ions floating around, it's harder for that bubble to do what? Get to the surface, which means it requires more energy, which is why if I add salt to my water, it's going to boil at a higher temperature. Now, Sunday afternoon, your family's going to have spaghetti, right? What's the very first thing your mom does? What? What'd you say?
I'll put salt in them
Okay, so why does she put salt in the water?
to flavor the noodles.
Okay. Jerk. Most people think it's to do what? Make the water boil. That is 100% not the truth. It actually makes the water, it actually takes the water what? Longer. Why? Because the boiling point's higher, it requires more energy. The thing you need to realize is that in order for you to truly change the boiling point, you would have to put so much salt in there, you could not eat the noodles. That's how much it would take to truly change it enough for it to matter. It's about flavor. It has nothing to do. People think that, but that is not true. Now, might it change it, a tenth of it? Yeah, it's going to change it a little bit, but is it truly enough to affect it? Not really. Are they some of those glasses? Are they some of those glasses? Yeah.
They're prescriptive. They just have the blue and white lens on it, so I don't get really bad.
Oh, okay. You're like the fifth student I've seen since Christmas have a pair of those. But you still wear glasses. These are just...
These are my prescription.
But I can see kids that wear... You can see... Can anybody see what I'm talking about and how you can tell that they're a different... Do they help? Because I've been thinking about it.
And I
Although...
have astigmatism, so it helps a lot.
Oh, gotcha. I don't know if I could wear glasses all the time anyway. Alrighty, so does that make any sense? Okay, now from there. Alright, next thing we're going to talk about is hyper and hypo. Hyper and hypo. Anybody know what those two things refer to? Okay, so comes from what? Where did you learn that? Where? Health science, right? We're talking mainly biology stuff. Now, I don't know if you guys realize this, but this class was designed for one thing when they started it. And that was for kids that are pre-med, pre-dental, pre-nursing, any of those things. This was a health science class, right? It was really designed to weed people out and make them realize, yeah, I'm never going to be a doctor. Like, that's fact, okay? And if you'll notice, you know, if you'd read the chapters, even though no one does, every chapter has a section on the health field. You ever notice that? Now, granted, very few of those show up on the test. In fact, I can think of maybe 2 tests so far that have had one of those questions. Well, this one does, and it goes with this. Now, hypertonic, and hypotonic. Now, what we're going to talk about is we're going to talk about as they apply to blood. Okay? What would happen if I put blood in a hypertonic solution? Does anybody know? So, what, Buxton, what were you saying hypertonic meant?
It's like above or excessive.
Excessive, what do you mean?
Like
Amounts, okay? So, if I put a blood cell, like we're talking about a red blood cell, little donut looking, we all know little donut looking thing, right? Okay? If I put that in a hypertonic solution, what's going to happen? Does anybody know? Backwards. Yeah, so water will flow out of the cell, and the cell will, does anybody know what the word for that is? Did you watch my video?
Well, I didn't in your class, and then I
Oh! Yeah, I forget. You're like Kaiser now. It's called crenation. It crenates, which basically means it shrivels up. And it will crenate. Okay, don't tell them the next one. Hypotonic is what Bingham said. Water's going to flow where? Will flow into the cell. And the cell will, anybody know what it's called? It starts with an L. Kids used to get them in their hair. Nobody? Lice. It will lice. It means ruptures, splits, bursts open. Okay? And it does that. Now, when I was in college, we did this with onions. You peel off a layer of onion, you put it under a magnifying glass, and you would pass salt water across it, and you would literally see the cell shrivel up as all its fluid went out to try to dilute it. Because it always goes from a low concentration to a high to try to dilute it, to make them equal, right? So then the cell would shrink up, right? Then you would take the same cell and you would pass pure water across it, right? Well, as I pass that pure water across, what would it do? It would absorb that water and get bigger and bigger and bigger and bigger until it just burst wide open. Okay? Now, let me show you an example of this. Every year I do this. This is the first year in like 5 or 6 that hasn't worked. I think it's simply because I didn't start fast enough. But, all right, now, everybody know what that is? Peach. Okay, it's a peach that is basically becoming what? It's crenating itself as it is basically becoming freeze-dried. And usually by this time it's nothing but the pit and a little bit of skin, right? But what that means is it means that its skin is a what? What would we call it? Anybody know? Medical term? Close? More? Make that longer. Say that louder. A semi-permeable membrane that lets the water out, right? That's why it's drying up. So what I used to do is once this gets really small, I put it in a beaker of water. Now over a period of a couple of weeks, what does it do? It slowly rehydrates. Up until one year, it literally looked like the day was picked. It was crazy cool. Okay? But that's what happens with a semi-permeable membrane, is it allows that water to flow back and forth. Right now, is flowing out of the system. If I put this in pure water, it is going to flow back into the system to try to dilute the peach. And it's actually really cool. And if this ever gets small enough, we'll do it. If not, we won't. But yeah, frustrating. Last year's was really good. I mean, it really swelled up good. Now, with that, you got to talk about a semi-permeable membrane. Okay? So right here, this is a semi-permeable membrane. Semi-permeable membrane. Now, what I've got going here is this. Is you're going to have A and you're going to have B. Let's say they start out at the same level. Let's say that A is 0.75 molar. Excuse me, B is 1.5 molar. Let's say after 5 hours. 5 hours elapse. What am I going to have? Anybody know? What's going to happen here?
It's gonna flow from B to A.
It's going to flow from B to A. It's going to go from here to there. It actually flows the other way. It wants to dilute them. It wants to make them have the same what? Same concentration. Okay? So what will happen is water will flow this way. My B is going to be up here. My A is going to be down here. And it's going to do that until they reach basically like an equilibrium. And what would be my new concentration? They're going to equalize. How would I find that new concentration? Yeah, I'm going to divide by 2. I'm going to be 0.9 something, 0.925 or something. I'm guessing. Somebody add them together and divide them by 2. Oh yeah, 1 point something. 1.125? Is that what it would be? I don't know. Is that right? 1.125 molar and 1.125 molar. They would equalize. Okay? Which means they would now have what is referred to as the same osmotic pressure. Meaning they apply the same pressure on that thing. And what usually happens, and for what we're going to do, the only thing that passes through that membrane is water. The way the holes are in the membrane, just water can pass through. Now we're going to do this. It's really cool. You're going to take some dialysis tubing, and you're going to seal it off. You're going to fill it full of sugar water, right? That I've already prepared, and you're going to put it inside pure water. Okay, well, what's going to happen? What? The water's going to go into it, right? So you're going to find the mass of it before, and then you're going to find the mass of it after, and what better happen? It better get heavier. Okay, and then you're going to put pure water in it, and you're going to put it inside sugar water. What's going to happen? Water's going to flow out of it, and it's going to get smaller. Then you're going to do it with the prune. Who knows what a prune is? Prune is a dried plum. You're going to put it in pure water, and what's going to happen? Same thing. It's going to get bigger. Okay? Now, granted, you're not going to leave them in there long enough for it to, get big, but you will, through mass, be able to tell that it has gotten heavier as it's absorbed that water back into the cell walls. It's actually really cool. Okay? Alrighty, so from there. There. Oh, okay. Now, saturated. Anybody know what the term saturated means? Sorry. Nobody here has ever made rock candy? Not one person knows what saturated means. You're kidding me. Really? No one, Brad Geddes? You don't know what saturated means?
Isn't that like when the max amount of salt used can be dissolved or something?
Holding the maximum amount of solute under given conditions. Okay, so when I was a kid, we used to make candy all the time, right? You take your pan, you put it on the stove, and you dump a whole bunch of sugar in it. No matter how hard you stirred, all that sugar wouldn't what? It wouldn't dissolve until you did what? Heated it up, right? Once I heated it up, all that extra sugar would dissolve. Why? Now, what did we talk about the other day? Think like day one. If I want to increase my solubility, what do? I increase the temperature, right? Unless it's a gas, right? Gas was opposite, right? So I increase the temperature. So if something is saturated, it's only saturated under those conditions. So if I heat it up, now it's no longer saturated because I can get more sugar to dissolve. What happens if I cool it down and it's saturated? So I've got it at 100 degrees, and I've got as much sugar to dissolve in there as I can, and now I cool it down. Now it is supersaturated, which means it's actually doing what? Nobody? It's holding more than it should. That is the point at which I put my skewer in there, right? That skewer now gives all that sugar that's looking for a place to go a chance to come out of. No one ever did this as a kid? Are you kidding me? You're the first class that no one has done that. But you know what I'm talking about, right? Those sticks that had all those sugar crystals on them. They usually had some kind of flavoring, cinnamon or something in them, right? Well, yeah, cinnamon. No one else is, like, there's only two of us that know what the hell I'm talking about.
I know what you're talking
Yeah, we know what you're talking, we've just never done this.
Holy shit. It is. It's looking good right now. You guys got to get out more. Or I guess stay home more. Something. Jeez. Did you just say, I've got to get out more? I was a kid. Was that you, Ben? Now look. So you got to understand, unsaturated simply means it could hold more. Saturated means it's holding as much as it can. Supersaturated means it's holding more than it should. But it never determines a specific amount. Like I can't say 100 grams. Because that 100 grams is going to change as soon as I do what? Change the temperature. So you got to understand that saturated simply means as much as it can hold. It doesn't mean a specific value. Okay? And this is what I wrote. I literally wrote, does not mean a specific value. And I wrote that down yesterday morning, so I'm going to assume it means something important. Okay? All right. Now, from there, all right. Okay, now we're going to do a couple of questions straight off. I mean, not straight, but very similar to what's going to be on the test. Okay? So there's the hardest kind of problem I ran into is this one we're going to do right now, because it requires the use of multiple equations that we talked about the other day. And it says, what is the molarity wait a minute, it's not Ca, it's just CCl4, sorry. Just CCl4. Now, like I said, probably the hardest type of problem you're going to run into. Now, problem is because they want me to find molarity, right? But they gave me weight to volume. Okay? Now, if you remember, weight to volume percent was what? And remember the equation for weight to volume percent?
Mass of solute, volume of solution.
Mass of the solute, but it's got to be in what? Grams over volume solution, right? And that was in milliliters, right?
Times 100.
Times 100, okay? Times 100. Now, what I usually do is this. Is I say, well, really, there's three things here, right? I got 1, I got 2, I got 3, correct? If I want to solve this, they have to do what? They have to give me 2, right? What's wrong with that problem then? They only give me one value, okay? So, what this requires, okay, it requires you to must make an assumption, okay? And if you know how to make the right assumption, it makes the problem really easy. Now, this is what you do. Anytime you run into a problem like this, that is missing that value, you assume you have 1,000 milliliters. Anybody know why I want to assume I have 1,000 milliliters? What? We're actually going to do it differently than that, and we're going to take care of that percentage already. But what does 1,000 milliliters also equal? 1 liter, right? What did it ask me to find in the end? Molarity, right? What is molarity measured in? Moles per liter. So that 1,000 milliliters is going to work here, and then I'm also going to be able to use it in my next step as a 1. It makes the math really easy. Now, so if I assume I have 1,000 milliliters of solution, this problem becomes 17.5% equals, let's just say X grams over 1,000 milliliters times 100, right? Now, what I do is I just say, I don't need to worry about this. I simply say, that 100 is just going to make this what? Yeah, doesn't that just make that 0.175? Right? Just like I divided that 100 over. Now what am I going to do to solve for X? I'm going to times it by 1,000, right? Times it by 1,000, times it by 1,000. That's going to tell me that X grams is equal to what? Isn't it just 175 grams?
Yeah.
Isn't 1,000 times 0.175 175? That's 175 grams of what? CCl4. CCl4. Now, I've got my grams. The problem asked me to calculate my what though? My molarity. Well, who remembers what molarity is? It's moles over liters, right? Moles over liters. Well, because of what we assumed, we already know that I have what? 1 liter. How many moles do I have?
Yeah, 0.879 moles.
0.879 moles. Did you just like whip that out or what?
No, I haven't checked.
No, like where did that come from?
Oh, the moles.
Oh, you mean I've got to go back to this step and do what?
The more mass divided.
Yeah, convert from grams to moles, right? So I'm going to take this step, times it by 1 mole of CCl4 for every, what was its molar mass, Richards?
153.8.
823 grams of CCl4, right? That puts me in moles now, right? Well, that divided by that is going to give me a what? So just 0.879 molar CCl4. Oh no, I forgot to divide it. When I divide that, what do I get? No, I'm going to divide that by 1 still, don't I?
Yeah.
Divide by 1 is the same.
Only if it's bigger than 1.
I don't think so.
Wait a minute.
Yeah.
Yeah, wait a minute. This isn't right then. This is not the right number.
Yeah,
Because wouldn't it be bigger?
5 over 150.
You did it backwards. I'm going, that's not right. Yeah.
Bigger.
That's what I was doing. I was looking at the answer going, well, that can't be right. Okay, yeah. What's this number? Sorry, Bingham. I was losing my mind for a minute, wasn't I? What's this number?
1.14.
1.14 moles. Now I divide it by 1, it's 1.14. That's why I wrote it down the first time. 1.14 molar CCl4. Okay? Anytime they do not give you a volume, what do? Assume 1,000 milliliters because that translates to molarity as 1 liter. And it makes the math really easy. Okay? Alrighty, so the only other thing I want to talk about is these two terms. When they say the term salt or they use the term a salt. Anybody know the difference between salt and a salt? Now, a salt is simply any ionic compound. Salt means what? NaCl. Okay? There's lots of salts out there, right? Okay, because there's lots of ionic compounds. There's only one thing that is table salt, and that is NaCl. Okay, make sure you understand the difference, because that chart over there, talks about salts. Well, they're just talking about ionic compounds. But if they use the term just salt, they're talking about NaCl. Okay? So just something to think about. Okay? Questions? Anybody? Oh, wait. I'm still got like 58 people that haven't even started AA yet. Anybody got any questions? Remember how we talked the other day about how you don't know what you don't know because you don't do any of the homework? Yeah, that's like half of you still. I don't know what it's going to take to get you to do something. Yo.
I actually have a question.
Sweet, get it out.
I also had a question when we were, like how the, I forget what I'm trying to remember. Oh, like, so CaCl2, how that broke down into 1Ca2.
Because you can't ever, when you've got ionic compounds, they're going to split down into total ions. They will never stay Cl2 together, ever. Okay, yeah, that's if it's like it's a gas. But if it's a solid, it's going to split up into Cl negative ions, multiples.
Okay.
Does that make sense?
And then the 2 from the Cl goes up to the...
Exactly, the 2 Cl negatives, Ca2 positive, that whole drop and swap stuff. So what was your homework question?
I'm still trying to get there.
Okay.
I should have logged in.
Nobody else, is anybody besides Garrett done the homework? Get us? You've had to have done some of it, right? Any questions? I should have answered what was left on the Learn Smarts today, so I've covered everything that's on the test, that is. There are probably a couple of homework questions that I didn't address because they're not where? They're on the test. I'm not going to spend a bunch of time teaching something we're not going to be tested on.
Yeah, I'm almost there.
I have 51 that haven't even started 8A yet. That's usually the one they do first. Like 78 that haven't started S yet. Now you know why teachers get frustrated. Especially teachers in a college class. Now you know why that corner of that desk, that's awful tempting sometimes. Exactly. Yeah, thank you all for making me want to do that. I appreciate that.
Okay.
Bunch of jerks. Yeah.
We can still do this, but I think you already answered it today. But in comparing a 5.8 molar NaCl solution and a 5.8 molar CaCl2 solution,
Huh. Wow, that looks
familiar?
really shockingly almost familiar, doesn't it?
Which solution has the higher boiling point, melting point, osmotic pressure, and vapor pressure at a given temperature?
Okay, now, obviously this is a what? I get 3 ions here. I only get 2 ions there, right? This one will have the highest boiling point. It's going to have the lowest freezing point. What were the other 2?
Osmotic pressure and vapor pressure.
Okay, so vapor pressure, the more it has, the lower the vapor pressure. So this, as long as these are the same. Now you got to understand, I can only compare these if these are both the same.
Yeah.
Do you know what I'm saying? Because if they're not, then I got to times it out and do a bunch of math. But on the surface, if these are the same, all I've got to look at is number of ions, right? So this one would have the higher boiling point. It would have the higher freezing, or actually the lower freezing point, because it's going to affect it the most, right? It would have the lower freezing point, and then what were the others?
Osmotic pressure and vapor pressure.
Okay, so osmotic pressure is the pressure I exert back. If you go, there's actually a really good little snippet on this. Let me find it so I can. Where's it at? Osmotic pressure right here. Okay, so if you look on page 298, okay, the osmotic pressure is the pressure that prevents the flow of additional solvent into a solution on one side of a semi-permeable membrane, right? So when you look at this, okay, if I've got, like if I go back to this, right, and I look at this, and I've got, and I look at that, I say these are my two things, right? Now, clearly, this one has a higher concentration, right? So this one would have a higher molarity. This one would have a lower molarity, right? So when it says that, here we go. So here's what I wanted to read. It says, an increased volume of whatever the solute is creates increased pressure on one side of the membrane. Okay? So if I were to look at that, I've got more here, right? Which means this one then is going to have a higher what? But it's going to have a higher, because it says, again, listen to this, the increased volume of the solute, which is the more dots, right, creates increased pressure on one side of the membrane. Okay? When the increased pressure gets to a certain point, it prevents more water movement to further dilute the glucose solution. Okay? So when I look at this, it would be, if you look at it, how would I put this? Let's look at it this way. So the greater number of particles, I put it this way, the greater osmotic pressure. Okay? So again, if I look at these two, this has 3, that has 2, this one is also going to have a higher osmotic pressure, right? Okay? And then what was the other question?
Vapor pressure?
Vapor pressure?
Yeah. And you said that was going to be lower.
Backwards, yes.
Yeah.
This would have a lower vapor pressure. Lower vapor pressure, simply because there's less water in there to escape. It's going to require more. And it makes sense, because the more I have, the more heat, going back to the salt water, right? The more heat I've got to put in, it's got a lower vapor pressure. Does that make sense?
Yeah.
And that's probably where I got that example from, which is, you know what I'm talking about? That problem we did, that's probably where I got that example from, was those 2 chemicals. Okay? I would say what number, but that's a different number for everybody. So, okay? Okay. Use your time wisely.